We'll show the mechanics of the correlation coefficient, which is a number that shows the linear association between two continuous variables. Can you use a tape measure to weigh a bear? Why would you want to weigh a bear? Bears are like the apex predator, maybe a keystone species of certain environments. However healthy bears are, that's how healthy the woods are. But weighing a bear would be really hard to do. I don't know how I would weigh a bear. I'd probably shoot it, not kill it, but I would shoot it, tranquilize it, and then I would try to pick it up. Then I would put it on some sort of scale. And then before it woke up, I would write down its weight and try to take it off the scale and put it back where I found it and then run away as fast as I could. But bears are big. You might get a bear that weighs 416 pounds. It's manageable, a little unwieldy, but you could pick that up and put on a scale if you had to. But maybe there's an easier way to see how healthy a bear is. But can you estimate a bear's weight from its length? Well, again, it'd be easy. You shoot the bear first, and then when it's laying there, run up, take a tape measure, measure how long it is, write down the length, and run away. Or maybe you don't even have to shoot it at all. Maybe you could take a picture of the bear standing next to some sort of tape measure. You ever go to 7-Eleven and notice when you leave the door that there's a little strip on the side of the door that says 4 feet, 5 feet, 6 feet? So if someone robs the store, they can take a picture of them when they run out and see how tall they are. Maybe you could do the same thing with a bear. Put a little thing of honey or something up high, see how tall the bear is. Is there a relationship between a bear's length and its weight? Two continuous variables. First step, look at the data. Well, it looks like I have some short bears who aren't that heavy. And it looks like I have some tall bears who are pretty heavy. Now, it's not perfect. These bears are the same height, 72 inches, same as me. And their weight, pretty different. A lot of variability there. But do we see any sort of patterns? Is there a relationship between how long or how tall a bear is and how much it weighs? We could draw a picture. This is a scatter plot. Here, how long it is. Here's a bear. How heavy it is. You draw a bunch of points. Here's a bear. Here's a bear. Here's a bear. Can we quantify this relationship in some way? The answer is yes. It's called the correlation coefficient, or R. The correlation coefficient, by definition, is the linear relationship between two continuous variables. People use the word correlation to mean a lot of different things. They might say correlation when they mean relationship or association. Don't do that. Correlation is a measure of the linear association between two continuous variables. And it has two parts. It has a sign. A correlation can be positive or negative. And then it has a number. It's a unitless measure. It can go from -1 to +1. -1 is a perfect correlation. As your X variable increases, your Y variable decreases by the exact amount. A correlation of +1 is similar. It's a perfect linear relationship. You can draw a line right through all the points. This is like physics. The laws of the universe have perfect correlations. But when we study free-range human beings, there's all sorts of noise. There's all sorts of other variables that go into the associations that we're looking at. So we're not going to see perfect correlations. We might see tight, strong correlations like 0.8 or 0.6. You have to look closely though to see the difference between 0.8 and 0.6 or 0.4. But you'll get practice on doing this. There's all sorts of great resources that'll show you a picture of a scatter plot and make you guess what the correlation coefficient is. If the correlation coefficient is 0, it looks like this. What is that? That's like just a cloud or a blob or just a bunch of like random ink sort of thrown at the board that doesn't have any sort of pattern to it. That's a correlation of 0. When we measure these bears, we're not interested in these individual bears. We're interested in talking about what's going on in the population. So the correlation coefficient is a population parameter, and we use letter rho for that. And it measures what's called the covariance. How do X and Y vary together? And what we're going to do with the correlation coefficient is take the x values, in this case it's the length, see how they differ from the mean. And then we'll take the y values, which is the weight, and see how they differ from the mean, and see how they vary together. And the denominator here is interesting because when we divide by the standard deviations, we will turn this into a unitless measure that runs from -1 to 1. I'll show you how this works. When we measure this in our sample, there's our letter R. Carl Pearson was one of the statisticians who did early work on this. So this is called the Pearson's correlation coefficient. And what you see here is in the numerator, you take for each individual bear, that I there stands for the individual. For each individual bear, you take, I almost said his, it, you take their length, and you see how far away it is from the mean length. And then you see for that bear's weight, how far away it is from the mean weight. You multiply these two things together, and you do this for every single bear, and you add them up. So there's our Greek letter sigma again, which stands for sum. Then what you do is you divide by the standard deviation of x and the standard deviation of y, and this brings us back into a unitless measure. Let's see how this works. Here's our bears. This is just an Excel spreadsheet. I take each bear, its weight and its length, and I see how far away it is from the mean. So this first row, this little baby bear, lighter than average, shorter than average, negative, negative, negative. When I multiply negative by negative, I get this positive. This next bear is heavier than average, taller than average. When I multiply those two things, I get this. I multiply all these together for each individual bear, and then I add them up. That's my numerator. And then in the denominator, I take the standard deviation of x and the standard deviation of y, and that goes in right here. Plug this in, and I get the correlation coefficient. And for these bears, the correlation between height and weight is pretty tight, pretty strong, 0.89. It's interesting that the numerator of this can be either positive or negative. When you multiply a very tall bear who is very heavy, you'll get positive times positive, and you'll get a positive result. If you multiply for a very short bear who is very light, you'll get negative, negative, and negative times negative is positive. So we start to get a sense of how these bears sort of contribute. If those two things run along together, you're going to get a bunch of positives, you get a positive number. In contrast, if you had a cloud of points that looked something like this, you'll see that bears who were really tall, like this guy right here, he's tall for a bear, but he's also pretty light for a bear. So you get positive times negative, and that would be a negative. So this is a picture of what would be a negative correlation, whereas this would be a positive correlation. And this is what determines the sign of R. If you get a lot of points, relatively, a lot of points up here and down here, then you're going to see a positive correlation. One way you can help figure out what the correlation is you can look at the empty space. See where all the empty space is in this? It's in this here and this here. And that's a hint that the points must be here, and we're going to have a positive correlation. We'll study the correlation coefficient in more detail, but for now, take a look at a bunch of different data sets. See if you can guess what the correlation is.